In order to navigate a labyrinth or maze, one of the most basic things we're going to have to make our robot do is drive down a hallway or a corridor. And the robot's going to have to do that without bumping into walls. Ideally, the robot's going to be able to do that by driving right down the center of this corridor. In order to make that happen, we're going to have to use a technique called proportional control. The way we're going to implement that is we're going to take this right hand sensor, the sensor on the right side, and we're going to compare it to the sensor on the left side. And we're going to try and keep those values equal. We're going to try and make the difference between those values 0. So that's the first step of proportional control. We're going to come up with an error value that's based on the right sensor minus the left sensor. The next step of proportional control is we're going to feed that information back into the motors. And we're going to do it in this way. The left servo is going to have a power level of 50% most of the time, but we're going to add the error to that servo. So that if this error is greater than 0, then the left servo will go more than 50%. And if the error is less than 0, if it's a negative number, then the left servo will actually be powered less than 50%. The right servo, on the other hand, will be just the opposite. If the error is a positive number, then the right servo will actually slow down. It'll be 50% minus that error. And if the error is negative, well then 50% minus a negative number is actually going to add to the 50%, making the right servo turn a little bit faster. To see how this works out, let's see what the situation is at the very beginning, where the mouse starts out with an error of 0. These distances are equal. That means the left motor is powered at 50 and the right motor is powered at 50. But then, because robots never go perfectly straight, our robot wanders just a little bit, and it's a little bit closer to the left side now, in which case here the error is going to be, let's say, 10. This distance here now is bigger than the left sensor, and so we get an error that's positive. That's going to cause the motors to be powered at different levels. The left motor is now going to be powered with 50 plus the error, 60 here, while the right hand side motor is going to be underpowered. It's going to be 50 minus that 10, giving us a power level of 40. That's going to cause the robot to turn a little bit. This side's going a little bit faster, that side's going a little bit slower, and so the robot's going to turn to the right a little bit until it gets to the point where it's back in the middle and the error levels, the left error and the right error, are back to being equal. So we have an error of 0, and the motor powers are back to 50 and 50. It's worth mentioning that in order to use proportional control, the motors must be underpowered to begin with, because we can't add extra power to a motor that's already at full power. Adding proportional control to the Nano mouse is relatively simple. It involves just a few lines of code. To start with, I'm going to go to the Nano mouse motors file, and I'm going to copy the forward function. I'm going to paste it at the very bottom, and rename it to forward proportional. This function will take one argument, which will be the error term, or however much the robot deviates from the desired path. Now here we're going to see two things that are counterintuitive. The first is, earlier I explained that we would be adding to the power level of the left motor in the event that the error term was positive. That was because we were discussing the sensors as though they detect a distance, and the further the distance, the larger the number. But that's actually not how our proximity sensors work. The more reflection, the higher the number. And the greater reflection occurs when the distance is actually closer. So we're actually going to be subtracting the error term right here. Now, you would think that would mean we'd add the error term here, but you have to remember that the right servo motor's orientation is actually opposite that of the left servo motor, so we're actually going to be doing the same thing here. Intuitively, we can understand this as the left servo motors, the error term is counteracting the power, and here the error term is working with the power. So they are doing opposite things. Once we have this forward proportional function written, it's time to use it. So I'm going to go back to our main file, and I'm going to scoot on down to the loop function of our code, and I'm going to call the function. I'm going to do that by saying motors dot forward proportional, and then I have to supply it with an error term, and I'm going to do that by saying sensors dot right minus sensors dot left. In order for this code to work, the sensor values have to be accurate, which means I actually have to run the sense function. So right before this line of code, I'm going to write sensors dot sense. That's all it takes to modify our robot so that it reacts to the walls and drives straight down the hallway or straight down the corridor. Let's see how it works. Here you can see proportional control in action in slow motion as the robot starts out oriented incorrectly, heads towards the wall, and then corrects its orientation ever so slightly. Here we can see proportional control adjust the robot's heading again. My only criticism is that it's taking a little longer for this algorithm to kick in than I would like.